You're in motion right now. A whole lot of motion. But what does that even mean? Well, today, we're going to unravel the entire story of motion, not with boring textbook definitions, but with one single journey that's going to make everything just click. So let's dive right in.
So let's start with a really simple question. Right now, as you're sitting there watching this, are you moving? I mean, you probably feel like you're completely still, don't you? But in the world of physics, well, the answer isn't quite that simple.
And this gets right to the heart of it. Check this out. On the left, from their own point of view, Chintu and his girlfriend are at rest. They're walking along at the exact same speed, so to each other it feels like they aren't moving at all. But from the perspective of our observer, Mintu Lal, over on the right, they are very clearly in motion. And this right here reveals the first, most important rule of physics. Motion is always relative to an observer.
Okay, so to properly describe any kind of journey, physics uses two totally different languages. And trust me, understanding these two is the key to unlocking everything else that follows.
First up, we've got scalar. A scalar quantity is super simple. It only has magnitude, which is just a fancy word for an amount or a number. Think of something like temperature or your mass. It's just a number, right? There's no direction attached to it.
And the second language is vector. Now this is where things get a bit more specific. A vector quantity has that magnitude, that number we just talked about, but it also has a direction. And that direction, that's the crucial extra piece of information.
Here's an absolutely perfect way to think about the difference. On the left, studying for 8 hours. That's a scalar. It's just an amount of time. But look at the right side, studying the right books for 8 hours. Now that's a vector. You've got the magnitude, 8 hours, and a clear direction, the right books. You see? One is just plain effort. The other is effective effort. Direction matters a lot.
So, let's apply these new languages to Chintu's journey to school. We're about to see how scalar and vector can describe his path in two completely different ways.
First, let's talk about distance. Think of this as the backbencher's route. It's the total actual path you travel. You know, after school, maybe you wander over to a friend's house, then you go to a shop, and then you finally head home. You've covered a ton of ground. That entire long, winding journey, that's your distance. But then, there's displacement. This is the topper's shortcut. A topper leaves school and goes straight home, the shortest, most direct path possible. Displacement doesn't care about the long journey you actually took. It only cares about the straight line from your starting point to your ending point. That's it.
So let's break this down because this is the crucial part. Distance is a scalar. It's just a number, and it's always positive because you're always covering some ground. Displacement, on the other hand, is a vector. It has direction. And because of that, it can be positive, negative, or even zero, because it only cares about where you start and where you end.
Okay, time to put this to the test. Let's say Chintu runs one full lap around a 400-meter track. His distance is obviously 400 meters, but what is his displacement? Think about it for a second. Where did he start and where did he end?
The answer is a big, fat 0. And you might be asking, how? Well, remember, displacement only cares about the start and end points. Since he finished in the exact same spot where he started, the shortest path between his start and his end is nothing. He has been displaced 0 meters, even after all that running. Okay, we've figured out the path Chintu takes. Now let's talk about how fast he's actually moving along that path. And just like before, there are two different ways to describe this, a scalar way and a vector way. So, speed is our scalar. It's simply the distance you travel divided by the time it took. Easy enough? Velocity, that's our vector. It's your displacement divided by time. You see the connection here? Speed is tied to distance and velocity is tied to displacement. And that means velocity always has a direction. And here is where that little distinction becomes incredibly important. Picture this. A car is driving in a perfect circle. The speedometer is locked, not changing one bit, at a constant 50 kilometers per hour. So its speed is constant. But is its velocity constant?
And the answer is a definite no. Why? Because the car is constantly turning, its direction is changing every single moment. And since velocity includes direction, any change in direction means a change in velocity, even if that number on the speedometer never ever budges.
All right, now we get to the really exciting part of any journey. What happens when your velocity doesn't stay constant? What do we call it when you hit the gas and speed up, or slam on the brakes and slow down? Well, that, my friends, is acceleration.
So let's imagine Chintu's dad is driving his legendary Alto car. They're just starting their trip,
cruising along at a steady 20 kilometers per hour. This is what we'd call their initial velocity.
But then, out of nowhere, a Ferrari pulls up next to them. His dad's pride is on the line. You know how it is. So he slams the accelerator, pushing that little car all the way to 200 kilometers per hour. This massive change, from their starting speed to their final speed, is exactly what acceleration measures.
So, the official definition is that acceleration is the rate of change of velocity. It's not just about getting faster, it's about how quickly your speed or your direction is changing. Speeding up is positive acceleration. Hitting the brakes, well, that's negative acceleration, which we usually just call deceleration.
So, how do all these things, displacement, velocity, acceleration, all fit together? That's where the three equations of motion come in. Now, I know they can look kind of scary, but just think of them as physics cheat codes. If you have any three pieces of info about a journey, these equations can unlock all the rest. And to help you remember them, we've got a very unique story.
Okay, the first equation is V equals U plus AT. To remember this, picture a little story about Vanita and Umesh. Vanita stands for V, Umesh stands for U, and AT sounds a lot like atom. So the story goes, Vanita met Umesh, who had an atom bomb. Simple as that. V equals U plus AT.
The story continues. The second equation involves their friend, Shubham. The S stands for Shubham. He has a unit test, which gives us UT. But he's worried. Why? Because he's thinking about that half atom bomb from before. Atom is AT, and the bomb is kind of round, right? Like a squared symbol. So we get Shubham's unit test was on, but he was worried about the half atom bomb. S equals UT plus half AT squared.
And for our last equation, Vanita and Umesh have a huge fight. That's the minus sign. So V squared minus U squared. To make up, Umesh says something sweet to Vanita in Hindi, Tu mera asma, which means you are my sky. Now the word tu sounds just like the number 2, and asma sounds a lot like ASA. So the fight, V squared minus U squared equals 2 asma, 2 AS. It's a bit of a stretch, I know, but you're not going to forget it. And that brings our entire journey full circle, right back to where we started. We learned that all motion depends on your point of view. So I'll leave you with this to think about. If everything is moving relative to something else, I mean, the Earth is spinning, the Sun is orbiting the galaxy is flying through space, can anything in the entire universe ever be described as truly, absolutely still? Thanks for coming along on the